Greetings, greetings. Welcome to the lesson on probability from grade 10 mathematics content. We do have the two types of probabilities. The first one, we have theoretical probability. The theoretical probability, it is measured based on reasoning and past experiences. What you know that it will happen based on your experience. For example, there is a show called Generations. We all know that the show is broadcasted on Monday, to be precise. So theoretically, we know that every Monday we will see Generations. And another example there, it's actually a question that says, will you see the sun at night? If it's possible, can you see the sun at night? I guess we all know that the thing that we can only see at night is the moon and the stars. So therefore we cannot see the sun at night. Hence the probability that the sun will occur at night is 0. And then before that, the probability that generation will be broadcasted on Monday, it is actually 100%, it is certain. So that is the probability. How is the chance of that event to occur? So generation will be broadcasted on Monday, it's 100%. We will never see the sun at night, so it is impossible. Let's say unrealistic, it's impossible. The probability for sun to occur at night, it's impossible. Now we know that the chance of getting a tail when you are spinning a coin is 1/2, which is a 50% chance. That when you are tossing a coin and flipping it on one side, the chance of getting a tail, it is 1/2. Hence, those examples, they highlight the fact that there are probabilities that we know theoretically based on our experience and some of the reasoning that I've just highlighted. We do have the other one, experimental probability, which is based on performing random experiment or trials as you wish. So you will be performing the trials to see if you will get the specified percentage. For example, let's say you toss a coin, the same coin that you know that a chance to get a tail is 50%, a chance to get a head is 50%. And then you cause the coin for 10 times and record the results. Now let's say you record the results and then you realize that maybe tail only occur twice as you're flipping the coin and maybe landing it on one side. And then you will say that a head would occur 8 times. So an experimental probability, it is said to be sometimes biased because one outcome would occur more than the other. So it doesn't necessarily mean that the chance is not 50% of getting a tail to head, because once you get a tail twice after you just flip the coin 10 times, it would only mean that the chance of getting a tail, it is 20%, of which is not unrealistic. So the experimental probability, it is sometimes biased. But this is just an introduction for you to know that the probability, it is something that you are either sure that it will occur or you are not sure what will occur. And then you can either prove that probability will occur through the experiment, and then the experiments, sometimes they are biased, because there is a definition of a bias in probability which says that it is when one outcome has occurred more than other outcomes. Oh well, I guess I should have started with the definitions, but it's okay. There are the concept clarifications. Let's clarify some of the few concepts that you are going to need to conceptualize before we move on with the lesson. Now we have the definition for a probability, which is denoted by the letter P in bracket A. So probability is defined as the number of the chance, or let's not say the number, it is the chance for an event to occur. Like how possible is the chance to occur? Like we have just stated in the previous slide there, that generation will occur. So we are certain that we will see the show on Monday, and then it's impossible. We know it's impossible to see the sun at night. So how is the chance? It is the measure of the chance for an event to occur. So we are just measuring the chances for an event to occur. So what is an event? An event is a set of outcome that we are interested in achieving. Like we just said there, can we achieve the sun at night? We were interested in achieving the sun at night, but it is possible. So the outcome, it is 0. So what is the outcome? The outcome is a single result for a random experiment. So let's say we are not experimenting, but we are exactly sure that we will see the show on Monday. So the result will be 100% because we are certain that we will see the generations show on Monday. So that is the outcome. Once we see the show that we have just assumed that it will appear on Monday, it just appeared. So that is the result, it is the outcome. The event is just seeing the show on Monday, and then we just seen the show on Monday, so we got the outcome after we had just set the event. Then let's move forward to the one that is commonly used, sample space, which is a set of the total number of possible outcomes. So the sample space there, 1, 2, 3, 4, 5, 6 is the one that we are going to use in the next slides, which is the sample space of rolling a die. So the sample space, we can therefore say the total number of possible outcomes when you are rolling a die. You can either get a 1, a 2, a 3, a 4, a 5, or 6. Therefore, the total number of those possible outcomes, you can easily count them there, 1 up to 6 is just 6. So the number of the sample space, the number of possible outcomes, the total number of all the possible outcomes, it is 6. Therefore, there it is n, which is equal to 6. Therefore, it is the sample space for rolling a die. Now, there is a possibility that an event can occur. It is calculated by that formula, which is NA over NS. NA, there we just said it is the outcome that we want to achieve. Let's say we want to get a number 2 when we are rolling a die. So the probability of getting the number 2 when we are rolling a die, we are just going to say 2 over the sample space, which is 6. Therefore, there below, let's look at the 2 examples. When we are rolling a die, and the chance to get an even number, it is 3 over 6. Even numbers are 2, 4, and 6. So the numbers that I just mentioned, there are 3 of them over the total number of the sample space, which is 6. So the probability of getting an even number, it is 3 over 6, which can then be simplified as 1 over 2. So the probability of getting an even number when you are rolling a die, it is 50%. So that is what we know theoretically so. And then another example, let's say we are rolling a die and we want to get a number 1. So the probability to get the number 1, it is 1 over 6, because there is only one on a die. There is only one number 1 on a die. So there is how a probability it is calculated, by dividing the outcome over the number of the total outcome. The outcome that we wish to achieve over the total number of the outcome. Simply an event over the sample space, or the outcome over the sample space rather. Probability of any event. Let's take note that the fact that probability lies between the numbers 0 and 1. We have there 0 over the sample space. For example, 0 over the sample space, it is when you want to get a 7 on a die, and we all know that the numbers that appear on a die are 0, not 0 actually, but 1 up to 6. So if we wish to get a number 7 on a die, the chances are 0. It is impossible to get the number 7 on a die because there is no number 7 on a die. So the probability starts from the impossibleness of the situation whereby you are wishing to achieve an outcome and it's not possible. Then there we have NA, which is the outcome over the sample space. Say we want to get 1 or even number or prime number or anything. You can simply divide by the outcome by the sample space. Then you will realize that the number because it is a fraction, it will always lie between 0 and 1, as long as the numerator is smaller than the denominator. You will get the number that is between 0 and 1. Then there it's the number when the number of the outcome is the same as the number of the sample space. Let's say we are rolling a die and we want to get the number that is greater than 0. Obviously 1 up to 6, they are all greater than 0. So the number of the outcome will be equal to the number of the sample space. Therefore, we will say 6 over 6 and then it is 1. Therefore, it is proven that probability lies between 0 and 1. We will further clarify it on the next slide. And then therefore, let's take note that when we calculate the number of the outcomes that are equal to the same number of the sample space. For example, therefore, we get 1 over 6 plus 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 1 over 6. Adding the 1 over 6 of the 1 over 6's, we get 6 over 6. Therefore, that simply means the number of the sample space is equal to the number of the outcome. Hence, the probability cannot be greater than 1. It's always between 0 and 1. Let's go to the next slide and clarify that. Looking at the numbers there, as I've explained in the previous slide, we have 1 over 2 plus 1 over 2. So let's say you are tossing a coin and then you know there are two sides of a coin. So when you add those outcomes will give you 2 over 2, and then the probability cannot be greater than that number. And then there we have 1 over 3. When we added the 1 over 3's, we get 3 over 3, which is a whole number, number 1. Therefore, we have a quarter. If we can add 4 quarters, 1 over 4 plus 1 over 4 plus 1 over 4 plus 1 over 4, it is 4 over 4, which gives us 1. So this is only the verification that a probability cannot be greater than 1. So as you can see there, it is stated there at the bottom, a probability of an event must always be between 0 and 1. That fact is very, very important, because we are going to need to utilize the fact that the probability cannot be greater than 1 to solve some of the problems. So take note of the fact that probability can never be less than 0. It can never be greater than 1. It is always between 0 and 1. Now on this slide, we see there is a Venn diagram, but you need to know the symbols, or as well as the names of the different types of the events on a Venn diagram. So let's take the first one. We can have two complementary events. Let's say we have event A or event B. For example, the complementary events, they are the events that are mutually exclusive and exhaustive. Exhaustive meaning that there is no outcome that is outside the event A or B. For example, let's say event A, we want the even numbers. The even numbers, when we are rolling a die, remember, it is 2, 4, and 6. All of the numbers, they are going to be in the circle A, 2, 4, and 6. Then event B, we can have, for example, odd numbers. Odd numbers will be our 1, 3, and 5. So we are going to realize that there is no intersection there. So if the events are said to be mutually exclusive, it simply means they do not agree on the same numbers, or they restrict intersection. Simply means that there are no numbers that can appear on both A and B. So if the events are said to be complementary, they are mutually exclusive, meaning there is no intersection, as well as exhaustive. Simply the numbers are all exhausted, they are all utilized. 1, 3, and 5 will appear on event B, and then 2, 4, and 6 will appear on event A. So we will never get a number outside event A or event B. We will see as we continue with the other examples. This is the first one, complementary events. Let's take note, they are mutually exclusive and exhaustive. Alright, then we have the other example, which are mutually exclusive events. As I've explained there, it's not complementary. This one can be mutually exclusive event. In this one, we can actually have a number outside the event A or B. So just take note that when the events are mutually exclusive, the intersection, it is restricted, meaning there is no A or B. We will never see the numbers that occur on the event A, and they will as well as appear on event B. Numbers will only appear on A, and they will be different from the numbers that appear on B. Like as I've stated on the previous example, if we take odd numbers on B, it will be 1, 3, and 5. And then even numbers will be 2, 4, and 6. So there will never be any number that appear on both A and B. So if you get that scenario, just know that the events A and B are mutually exclusive. They really restrict the intersection. There are no numbers that appear on both A and B. So above there, when the events are mutually exclusive, we don't have the probability to get A and B. It is 0 because the events are not intersecting. So we cannot get a number that appears on A and B. So the probability of getting any number or anything that appear on A and B, it is 0. So at the top there, it is a formula that is used to calculate the probability. So it says probability of A or B, which is the union, the number that can appear on A and the number that can appear all on B. So any number that can appear on A as well as B can be calculated by adding the probability of event A with the probability of event B, and actually minusing the probability of event A and B, which is the intersection. Now, if they are mutually exclusive, we don't have the intersection. So the intersection can be treated as 0. So below the Venn diagram there, let's see, we can therefore say P, probability of A or B, which is the union, all of the numbers that appear both sides, can be simply calculated by adding the probability of A as well as the probability of B. Since the intersection is not there, we can therefore say it is 0. Then the formula is simplified at the bottom there. Probability of A or B, it is equal to the probability of A plus B only. So for mutually exclusive events, the probability of A or B is equal to the sum of both probabilities of A as well as the probability of B. Not mutually exclusive, they really allow intersections. They are said to be inclusive. You will see the numbers that appear on A, they will also appear on event B. That way we can have an intersection. Let's say, for example, we want when we are rolling a die, we want the numbers that are greater than 2. Greater than 2 will have 3, 4, and 5. Those are the 3 numbers that are greater than 2, are 3, 4, and 5 for event A. Then for event B, let's say we are to look for an even number. So from the numbers of the die, the even numbers are 2, 4, and 6. So from the numbers that I've just mentioned on event A that are greater than 2, we will get the number 3, 4, and 5. Oh, I forgot to mention number 6. So there are 4 numbers on event A, and then how many numbers are on event B? There are 3 numbers because there are 3 even numbers. So the even numbers that are greater than 2 are only 2 of them. It is the numbers that are greater than 2, and they are even numbers as well. We will have 4 and 6. So in this case, we will have an intersection because we will have a number that appears on both A and B. And then let's go on to see the example so that you can further understand what is the inclusive events that are allowing the intersection, which are really not mutually exclusive. They allow the intersection, they don't restrict the intersection. So the probability of the events that are not mutually exclusive can be calculated by the formula there. Probability of A or B can be calculated as A plus B, the probability of A plus the probability of B minus the probability of A and B, because we would be having an intersection in this case when we are having events that are not mutually exclusive. So let's look at the example of the events that are not mutually exclusive so that you can further understand. Now here we are given a sample space of rolling a die. So if a roller die C, you can get actually numbers from 1 up to 6. So the numbers are 1, 2, 3, 4, 5, and 6. So that is the sample space of rolling a die. So a probability of having an event A there, if you can see, re tlhoka 1, 2, 3, and 4. That is our outcome that we want to achieve for event A, which are the numbers 1, 2, 3, and 4. And then event B, we have 3, 4, and 5. So let's take note of the numbers first. Event A, we have 4 outcomes that we are likely to achieve when we are rolling a die. So the probability of achieving event A, here it is 4 over 6, meaning for us to get 1, 2, 3, or 4, the probability is 4 over 6, which is the total number of the sample space, the total number of the outcomes that you can get when you are rolling a die. So let's check event B. We are willing to get 3, 4, and 5. So the probability to get event B, the numbers 3, 4, and 5, which are 3 numbers, it is 3 over 6. Remember, we are dividing by the total number of the outcomes, which is the sample space. And 3 over 6 simply means for us to get outcomes 3, 4, and 5, the probability is 3 over 6. Then let's look at the Venn diagram there. Now, looking at the Venn diagram, we can see there's an intersection. There's an intersection there because our events, event A and event B, they have 2 common outcomes, 2 common numbers, 3 and 4. 3 and 4, they are underlined there. So, for us to get event A, we have 3 and 4. For us to get event B, we have 3 and 4 as well. So those outcomes, they are intersecting because for us to get those 2 events, we need to highlight the fact that they both have the common numbers 3 and 4. Now the Venn diagram shows there event A. If you can look at the circle fully there, it is 1, 2, 3, and 4. And then if you can look at B, it is 3, 4, and 5. Now, for us to get A only, we can see there it is 1 and 2, which are event A only, that are not shared with event B. And for us to get event B only, we must get only 5. So 5 is the only number that appears on B only. 1 and 2 are the numbers that appear on event A only. Let's take note of the fact that we can count even the numbers in the circles of B as well. There are 3 numbers there, as I have stated at the top, and then in event A there are 4 numbers in the circle. So moving forward, let's look at the formula below. Formula below says P, probability of A or B, which is the union, looking at the numbers 1, 2, 3, 4, and 5. So simply means we must calculate the probability of A plus the probability of B minus the probability of A and B, which is the intersection. If we are looking for the probability of A or B, which is the union, we must consider the fact that there is an intersection and we are minusing the intersection, and you will see as I explain that why are we minusing the intersection there. Okay, looking at the probabilities of A and B, if we are to add them, it is 4 over 6 plus 3 over 6. Adding those probabilities alone, 4 over 6 plus 3 over 6 individually, you will get 7 over 6. That number, it is greater than 1, and which we are not regarding it as a probability number because we have explained there a probability must always be between 0 and 1. So 4 over 6 plus 3 over 6 will give us 7 over 6. So it is not a probable number, as it is greater than 1. So hence we are minusing by the intersection there, because they are both numbers that occur on A and B. So we cannot count them twice, meaning simply so. So we must minus the intersection to avoid counting the numbers in the intersection twice. So the numbers in the intersections are 2 and say over 6. It's 2 over 6. The numbers are 3 and 4, which are 2 in total. So there we have the formula that is fully 4 over 6 plus 3 over 6 minus 2 over 6. Hence, the probability for getting A or B, it is 5 over 6. We can then conclude it at the top. Looking at the top, let's count the numbers on event A. The numbers on event A, there are 4 numbers there. It's 1, 2, 3, and 4. And the numbers on event B, there are numbers 3, 4, and 5. So let's count 3 and 4 once. So we are going to get 1, 2, 3, and 4. Already we have counted 4 numbers on event A. Then on event B, we are going to count only the number 5. And that will make the total number of the outcomes 5 numbers. So we have 1, 2, 3, 4, and 5 over the sample space, which is 6. So hence the formula, it is proven to be correct, because we want the union A or B. The numbers that are likely to be selected in event A or B are 5 over the total number, which is 6. Then let's look at the number that does not appear in the event, in either event A or event B, which is the number 6 there. We haven't talked about the number 6. Here I have underlined the except 6. So if we are looking for the probability of A or B, we can therefore say it is 1, 2, 3, and 4, and 5. There are 5 numbers over the total 6, except number 6. So therefore there is an annotation there that says probability of A or B, but it says the probability that is not A or B. That simple, slash at the top, it's more like an exponent or such. Let's just indicate it there. There it is. Now it says the number that is not part of A or B, it is only one, which is the number 6. So it's more like a formula that we must use whenever we are required to find the probability of A or B if we are given the sample space that is like that of a die, whereby we are calculating the number of the probability that is A or B, and the numbers that are not in the circles there, they are not included in the events that we are wishing to achieve.